Okay, so I'm gonna keep going with the naming rules here. I think I'm gonna make two short videos of the remaining 18 slides just to cover what's left. So this is what we finished up with, just the simple single atom uh, ionic compound naming, and we're gonna start to layer on some additional rules here. So unfortunately, this is the start of a relatively substantial amount of memorizing, and given the short schedule we're on with this 5-week class, I think this is probably one of the biggest challenges that you have. So I encourage you to, as soon as possible, start putting in the time with flashcards or whatever it is that works for you to memorize things, to start with memorizing your polyatomic ions. And what you need to know is the formula, the charge, and the name. So again, refer back to handout 3. That has all the rules that you want to look at for all that, but of course it's also all here in the PowerPoint. So what I've done here is I've grouped the polyatomic ions by charge. That's a helpful thing to do to start with. And just you have the formula and the name. So like I said, flashcards, whatever you find works the best for you, that's what you want to start with. I think this is almost all of them. Maybe there's a couple more, but these are what I call the parent polyatomic ions. I think there's one non-parent on here with perchlorate, but we'll talk about that a little bit later. Something to see here to kind of guide your studies initially is a lot of these have an ATE ending. And for the most part, that's telling me, I think with the exception of hydroxide, which is kind of the outlier in a few different ways, that's telling me that they are oxygen-containing polyatomic ions. That's a pretty common thing we'll see for these, what I call parent polyatomic anions that we want to start with. Really, hydroxide is one of the few of the so-called parents that I would think about that doesn't follow this ATE ending rule. So we're still following the same general plan, which is we want to build neutral molecules overall. So I need to learn the charges for these polyatomic ions in order to make sense of that. With regard to hydroxide, just while we're here, the way I think about it is I'm just building hydroxide by combining O2 minus, that's the fixed charge for oxide, with 1H plus in order to make it OH1 minus, and that's how we get our polyatomic ion. Okay, so let's start to see how these are going to work, but like I said, kind of your first priority is going to be quickly learning these so that you can do all this sort of naming. So we're starting with new rules here, and the first rule is the same, right? We're going to write the name of a cation, and now we're going to work where the anion is a polyatomic ion. So if there's the good thing here is you don't change the name of the polyatomic ion, right? Nitrate is nitrate, sulfate is sulfate. You just put the endings on. So we're going to start by combining them with known cations of known charge, like the alkali earth metals and the alkali metals. So you'll start to see how that works. So I want to be able to identify my polyatomic ions, right? That's a big part of this. So this is nitrate, sulfate. Oh, there's sulfate again. And then hydroxide. Oops. And then again, hydroxide. I guess I'll write it just to complete it out. So the naming is pretty straightforward here, right? It's just going to be the name of the cation, sodium, nitrate, sodium sulfate, calcium sulfate, potassium hydroxide, and barium hydroxide. I don't think there's any capitalization rules on these, so you may see me write them capital or not capital. It doesn't matter, but that's how that goes. So, of course, you wouldn't be able to do this naming if you didn't know the charges on these. So, if we kind of follow what we were doing before, right, Na plus NO3 minus comes together as NaNO3, Na plus SO4 2 minus, then I need a 2 in front of the sodium to make that work, as Na2SO4. Okay, I think you get the idea there. Let's go to the last one. Barium's an alkaline earth metal, so it's barium 2 plus hydroxide. So, oops, I don't know why I put the negative charge on the wrong side. There we go. So now you should see that I need 2 hydroxides for every 1 barium. But if I have a polyatomic ion that I need to tell you there's more than one of, I've got to put the whole thing in parentheses and put a 2 outside of it. So well, that's how that goes, and that's something new I think you'll see here with the parentheses. So the next thing that we're going to deal with are all of the other possible cations. So we're going to go back to just having anions that are single elements and IDE as their name, but now we're going to use the metals that are in the center of the chart, what we call the transition metals, and these are cations that can have more than one possible charge. So not the alkali metals, not the alkaline earth metals, not silver, zinc, or aluminum, but all of the other ones. We need to write the charge as a Roman numeral in parentheses right after the name of that particular metal. So this requires kind of working backwards, so to say, to make sense of what's going on, and then you should be able to figure out how this all goes. So the approach that I have to these problems is I look at the anion, and that's Cl minus, and there's 3 of them, so that's going to be -3. So then what that means is I've got 1 chromium atom that needs to counteract that -3. So the only way that's going to work is if chromium is +3. So then when I name it, it's going to be, I'm going to keep doing that, chromium, then in parentheses, Roman numeral 3, chloride. And so I don't need trichloride, right? We don't use prefixes like that. The Roman numeral tells me, hey, chromium is +3, so knowing that chloride is -1, that tells me chromium 3 chloride means CrCl3. So now in our kind of pseudo-balanced equation, it's Cr3 plus 3Cl minus makes CrCl3. So then I want to work with the anion to start again, right? So that's fluoride. So we know that's F1 minus. There's 2 of them, so that's -2. And now my 1 copper atom needs to cover that. So it's going to be copper, Roman numeral 2, fluoride. And so now our equation would be Cu2 plus 2F minus makes CuF2. All right, next one. we've got oxygen. So this one's pretty straightforward, right? Because it's oxygen is -2 and there's one of them. So that means that the Fe also needs to be 2, except +2. So FeO is iron 2 oxide. So we're going to use the Roman numeral way to do all of these. So if you've used the ferrous and ferric or cuprous and cupric before, for the transition metals, we're going to use the Roman numeral naming. So here it's Fe2 plus O2 minus makes FeO. Okay, I hope this is making okay sense so far. Oxygen 2 minus, I guess I should have written 2 minus for this one too, not -2. And in this case, there are 2 of them, so that's -4. So the oxygen adds up to -4, meaning the titanium needs to be +4. So this one will become titanium 4 oxide. So now that's Ti4 plus 2 O2 minus makes TiO2. So the same principle. Okay, this next one we've got Cl3, and so we know that chlorine is -1. If there's 3 of them, that's -3. So that iron needs to be +3. So just like CrCl3 was chromium 3 chloride, this is now iron 3 chloride. Okay, so this would be Fe3 plus 3 Cl minus makes FeCl3. These last two, now we're getting to a situation where there are subscripts for both species. So the approach is still going to be the same, right? I'm going to say I have oxygen 2 minus, and there's 3 of them, so that's -6. But now I've got 2 irons to counteract that -6. So really that means 2 iron equals +6, right? Whatever the total negative charge is, the total positive needs to counteract that. So that means the iron needs to be +3. So this one is going to be iron, Roman numeral 3, oxide. So here it would be 2 Fe3 plus 3 oxygen 2 minus makes Fe2O3. And then the last one here, again, we've got subscripts for both species, so we need to kind of think about that in the same way. So nitrogen makes nitride. That's 1 to the left of oxygen, so it's 3 minus when it forms an anion. We've got 2 of them, so that's -6. So in this case, 3 coppers need to cover that +6 to make it neutral. So that means each copper, dividing both sides by 3, need to be +2. So this will be copper 2 nitride. And so now it's 3 Cu2 plus 2 N3 minus makes Cu3N2. Okay, so that'll take some work to get used to, but that's the general idea in terms of what it is we're trying to do with these. So more rules are coming, of course. Now what we're going to do is combine together anion as a polyatomic ion with cation that can have more than one possible charge. So again, once you've memorized the polyatomic ions, these parent polyatomic ions, because there's more of them, once you've done that, then this should make reasonable sense. So now what you should see are polyatomic anions for, oops, let me scoot up the rest of the way, for all of these. So we need to know those charges for now, probably just by looking at the chart, but eventually you want to memorize them. And so it'll be the same approach, right? NO3 is -1, and there's 3 of them, so that's -3. So the chromium needs to be +3. So it'll be chromium 3 nitrate. Sulfate is 2-. There's only 1 of them, so that's -2. I've got 1 copper to cover that, so it'll be copper Roman numeral 2. Remember, the Roman numeral indicates the charge on the cation, sulfate. Now I've got hydroxide, which is -1. There's 2 of them, so that's -2. 1 iron to counteract that, so it's just going to be iron 2 hydroxide. All right, let's see. Next one, we've got PO4. That's phosphate. It has a -3 charge. There's only 1 of them, so it's just -3 overall. So now my titanium just needs to cover that, so it has to be +3. So this is titanium 3 phosphate. All right, let's see, the next one, now I've got CN, that's cyanide, and it's -1. There's 4 of them, so that's -4. I've got 1 palladium atom to counteract that, so this is going to be palladium 4, and you can write III or IV, doesn't matter, palladium 4 cyanide. It's really the ones you've seen so far, hydroxide and cyanide are the IDE ending ones, the rest are ATE. Okay, what's this one? Carbonate, which is 2-, and there are 3 of them, so that's -6. But now, again, we've got a subscript for both of them, right? So now it's 2 irons that need to cover that -6, so kind of the same what we did before. We'd say, well, 2 iron equals +6, so iron equals +3, so it's just going to be iron 3 carbonate. Then this next one, this is the chlorate ion, ClO3-. There's 3 of them, so that's -3. And I've just got 1 chromium to counteract it, so chromium has to be +3, so this one will be chromium 3 chlorate. Okay, I think I'm going to stop just with that little chunk. The next steps get a little bit more complicated, so I think I'll take those on in the next video. Well, you know what? Let's keep going with this part. I'll do this slide and one more, I think. Yeah, we'll do that. Okay, so what you're going to see here is the parent ions we originally talked about, nitrate, sulfate, phosphate, but now each of them has a variation where we take away an oxygen. And what happens when we take away the oxygen is the ATE ending becomes an ITE ending. The charge stays the same, right? Nitrate is -1, so is nitrite. Sulfate is -2, so is sulfite. Phosphate is -3, so is phosphite. But the name is going to change. So if I learn my parent ions, then I just need to know when I change ATE to ITE, I'm going to drop 1 oxygen from the parent formula, but it's not going to change the charge. So let's do this page, and then I think that's probably a good place to stop. Then I'll have, what, 8 or 9 left to do. So now NO2 is NO2 minus, and it's called nitrite. So now this first one will just be sodium nitrite. No Roman numeral because sodium is always +1 as an alkali metal. SO3 2 minus, that's sulfite. And I'm pairing it with potassium, which is a +1. That's why there's 2 of them. So it's, again, no Roman numeral because it's an alkali metal. Potassium sulfite. Now I've got PO3 3 minus. Instead of phosphate, this is phosphite. And I'm pairing it with calcium, also, now this is an alkaline earth metal, but again, still no Roman numeral. Calcium phosphite. These next ones, so now with nickel and titanium and ruthenium, we're going to need to have our Roman numerals for these ones. So we'll see that in these next ones. So these are all transition metals, right? They're not alkali metals or alkaline earth metals. I confirmed that by looking at the periodic table. And they're not silver, zinc, or aluminum. So here I need to work backwards, right? Figure out the total negative charge in order to figure out the positive charge. I'm going to do that the whole semester. I've been doing it the whole year. NO2 is -1. There's 2 of them, so that's a total negative charge of -2. So the nickel needs to cover that, so it'll be nickel 2 nitrite. Now I've got SO3 2 minus sulfite, and there's 2 of them, so that's -4 overall. So that titanium needs to cover that -4, so it'll be titanium 4, and again, III or IV, fine, sulfite. Okay, next one is phosphite, that's 3 minus. There's only one of them, so it's just -3. So the ruthenium needs to be +3, so it'll be ruthenium 3 phosphite. And remember, you don't need to learn the names of the cations, right? Those are all given on the periodic table. Just need to be able to find them, and as you get better at looking at it, you'll know where to find them, but they're all there to look at. So looks like there's, I don't know, 7 or 8 more slides to look at, so I'll save those for the next video. But we're starting to layer on these rules, and again, I'm just kind of following along with the information in handout number 3. So yeah, let me stop here, and I'll do one last video to knock out the rest of the chapter, and then that'll be the end of our ionic compound naming, and then we'll head on to chapter 5.